Afternoon, everyone, and welcome back to your favorite math class of the day. Not even a chuckle. It's your only math class in the day. It's okay. I don't need you to laugh. I got a wife. She laughs at me just enough. Okay, so today we feature artwork from Mr. Adam Dale, and we appreciate his efforts. Thank you so much. I'm not really sure what this is supposed to be, but there it is, I guess. Yes, it's there. Bell work, he says. Okay. Yeah. All right. So yesterday we talked about exponential growth of bank accounts that's compounding, that has compounding interest. So your interest is calculated more than once per year. And we said that this was the formula for that. I'm just going to get you clued in. And what we said was that this was actually this was the formula where this came from. And this one was just what happens when you compound one time per year, where n equals 1. So that's what we learned in the last two sections. Okay, we learned this first because it's easier. And they go, oh, by the way, no, it's actually that. And when we talked about this yesterday, what we said was what you end up doing is calculating interest more than one time per year, so your interest has the ability to grow interest within the year. And if you think about it, the more of your interest that can grow interest in the same year, the more money you would have, right? So if it was compounding one time per year, your interest that you earn is literally just 1 plus r. But if it compounds, say, 4 times per year, where n is 4, then it's actually calculated 4 different times. You get 0.25 4 times, because 0.25 times 4 is 1. And this gets the mathematicians thinking way back in the day, and I mean a long time ago. I'm talking late 1600s, early 1700s. Some mathematicians sitting around scratching their heads going, well, we know that more compounding events equals more money. So if there was a way to make it so that the money was always compounding, there was an infinite number of compounds per year, then I should be able to maximize the growth rate within 1 year, regardless of what the interest rate is. Does that make sense to you guys? Great. So here's what we're going to do. We're going to explore that thought process just like those mathematicians did. And we'll look at it through the eyes of this, okay? The interest you earn, not the amount, I'm talking about the percentage. The percent of interest that you earn actually has nothing to do with this p-value. It's unimportant. If you have a 2.5% interest rate, you're going to earn 2.5% whether you deposited 100 or 100,000. It doesn't matter. A percent is a percent. Now, obviously, the amount of money is different, but the percent is the same. So we know that P has nothing to do with talking about the optimal number of compounding events. And since we're talking about in a single year, we could let T equal 1, which means we just have an n up here. And the best way to do this was how I was talking about, taking the 100% rate and splitting it across a number of events. So like I said, if you're compounding quarterly, then you have 4 of your 25s, right? But 4 25s equals 1. So what we do is we let the R value be 1, as if we were trying to earn 100% in that year. Allowing the number of compounding events to approach infinity actually leads us to something called continuous compounding. And that means all the time. Every time you think about it, yeah, you're gaining interest on your interest. Every moment. It never stops. It's constant. Unfortunately, the video is not going to be able to see what I'm going to do on Desmos. So I'm just going to go ahead and pause the video. So back to the video, now that Desmos has been done. And what we're going to do is we're going to look to see what our Y values are, what our actual compounding interest values are, as we let the number of compounding events get really big. And this table shows you it goes from 2 to 2.954. That's kind of a big jump. 2.705, okay, it's kind of big, I guess. And then 7, oh, you got to go to 2 decimals to see a difference. That difference didn't happen until 3 decimals. And again, I would have to go past 3 decimals to see the difference here. It seems as though this number is crashing towards somewhere around 2.718, doesn't it? Now, you can actually continue to find the decimal places, as many as you want. The number is irrational. It never stops with no pattern, like pi, or the golden ratio, or the square root of 2. You see, in mathematics, when we're dealing with an irrational number like that, the best thing we can do for it is give it a symbol, because you can't write out all of its values. The expression approaches this number, and the symbol we use to represent this number is the letter E, in lowercase e. So in mathematics, lowercase e is a number. 2.718828818 ... and it never ever stops. I'm hoping that you could see that I didn't just make up this number. I'm hoping you could see that this number was not created. That mathematicians in the late 1600s and early 1700s found this number, discovered this number, not created. And here's the thing. This is how they discovered it. Turns out it's all over mathematics. It's all over the place in the real world. What I'm getting at is, when I hear somebody ask a question, oh, is math created or is math discovered? It makes me want to punch him in the throat. Because obviously, it was discovered. Because if it was created, then why would this number show up in nature all over the place? Unless it was a discovery. It's a fundamental truth of the reality that we live in. And there are tons of numbers like it that you're unaware of, that are also irrational, but for some reason, part of our everyday life all over the place. Clearly, this number wasn't created. Just like how pi wasn't created. It's discovered. And because it shows up so often in reality and in nature, it just seems to be like a part of the fabric of the reality that we live, they called it the natural base E. So it's the natural base. I don't need you to know exact values of E. I just need you to know it's about 2.7-ish. Just like you know that pi is about 3.14-ish. E is about 2.72-ish. Okay? And you can get away with a lot of calculations just saying it's 2.72. It's not 2.72. But it's close. It's close. Okay? But because E is a number, it behaves like every other number that we know. It can be added, subtracted, multiplied, divide, raised to powers, rooted. Anything you could do with a number, you could do with E, because E is a number. Just, not a pretty number. So we give it this letter. Oh, and if you were curious why it's the letter E, it's because back in the late 1600s, early 1700s, it was commonplace when coming across these kinds of numbers to label them with vowels. Vowels. I was trying not to say variables. Vowels. So that's why they use the letter E. Yes, sir.
Whenever you're describing E saying it can be added, subtracted, multiplied, and divided, does the same thing apply to pi?
Yeah, absolutely. Like, what's pi plus pi? 2 pi.
Okay.
Yeah. Pi times pi? Pi squared. What does pi squared equal? I don't know. I know it's more than 9 because pi is more than 3. 3 times 3 is 9, But yeah, any numbers we can do that with. Just like the square root of 2. What's the square root of 2 plus the square root of 2? 2 times the square root of 2. What's 5 times the square root of 2? It's 5 root 2. What's the square root of 2 squared? 2. You see, yeah, it's a number. Its best representation is with a symbol. Okay, so let's simplify. We're not going to actually evaluate. I'm not going to pick up a calculator to see what these things actually equal. But I'm going to simplify these expressions that have base E in them. What is 2E plus 5E? And please don't overthink it. 7E. Yeah, that's it. What does 7 times E equal? I don't know. Something a little bit less than 21, I guess, because this number's smaller than 3. But who cares? The point is, right now, you know that you can add E. How about multiply? E to the 6th times E to the 4th. E to the 10th. It follows all the same rules. I don't know what E to the 10th is. I know it's a big number because I know 3 to the 10th is massive. So e to the 10th is pretty darn big. Here I have a product inside these parentheses, and these parentheses have an exponent. When you have a product with an exponent affecting the entire product, the way you handle that is you allow that exponent to apply to both of the two factors. I'm going to put this paper underneath here so my pen works better. There we go. Giving us a 2 to the 4th and an e to the 3rd to the 4th. And now we're just going to simplify. What is 2 to the 4th? 16. Lots of people, please, even those of you that are on your phones currently. What is e when you have a power to a power? What do you do with the exponents? Multiply. So I'll have e to the what here? 12. There it is. What is 16 e to the 12th? No clue. The point is, I know how to work with these things. And lastly, if there were no e's, it would just say 18 over 27. And you would reduce this. And he says it's 2/3. Absolutely correct. 18 and 27 can both be divided by 9 to get you 2/3. When you divide two numbers with the same base, what do you do with those exponents? Subtract. Where am I going to have my e's, though? Are they going to be in the top or in the bottom? In the top, because there's more of them in the top to begin with. Now you just subtract their exponents. 9 minus 6 is 3. And you're finished. There it is. It's just basic arithmetic. I'm showing you that it can be done even with something whose value you don't know. Kind of seems like it behaves like a variable, doesn't it? That's because variables are also numbers. They're just numbers you don't know the value of yet. But that's why they work the same way. All right. This is a typo. And it's because I got confused with rounding to 2 decimals or rounding to 3. It's 2.72 when you round to 2. It's 2.718 when you round to 3. So just make that 2 an 8 by putting a little slash through it. There, now it's an 8. Sorry about that. Guess what? Any exponential function, ab to the x, can be written in this form. A times e to the kx. It can be done anytime you want. But Mr. M, how is that possible? Well, let me show you. A moment ago, you all told me that when you have a power raised to a power, you multiply those exponents, correct? So what I see here is a multiplication in my exponent position. That means that can be taken apart. And it can be represented as a power to a power. Where b equals e to the k. And that's how you can write any exponential function as an exponential function that is base e. Are you comfortable with the whole idea of power to a power is multiply? So I took the multiplication apart, made it a power to power, and I'm just showing you a, x, x. Clearly, the thing inside the parentheses is the exponential base b. Cool with that idea? That's good, because I'm also going to make you see that it's also this. A, x, x. I know the letters don't match, but they hold down the same position. Exponential base, exponential base. We'll do that towards the end of the notes, okay? But I needed you to see how that works. And I actually have it right here in this box inside a box. Since e to the kx can be written as e to the k to the x, the exponential base b would equal e to the k. And this is for any appropriately chosen real number k. So k is a number. It'll be a number that you're told, or eventually a number you solve for. But the point is, it will have a value. K for constant. I'm pretty sure the Greek word for constant starts with a k, and that's why we use it. Okay. Anywho's it. How do you know if you're looking at an exponential growth or decay is the real question you should be curious about. The answer is, if k is positive, growth. If k is negative, decay. Let me prove. So how do we recognize something as growth? Recognize it as growth when the base is bigger than 1, right? And we recognize it as decay when the base is between 0 and 1. But I just told you that your base is e to the k. So let's see what happens if we raise e to a positive number. We can even use a small positive number if we want to. Can we agree that 0.1 is positive? If this was your function, I'm going to wager that e to the 0.1 is a number that is larger than 1. If it is, your exponential base is larger than 1, and you're looking at growth. On this calculator, e is hanging out right here above ln. On the battery-operated calculator, your ln button is over here, but you still have to use second to make it work. On the battery-operated calculator, you have to type the exponent first, and then do second ln. On this calculator, I do second ln. You'll notice it opened a set of parentheses for me. I'm going to type the exponent I want, and I'm going to close it. And I had better get a number that's larger than 1. How about that? So even though that exponent was really tiny, e to that really tiny power is still going to be greater than 1. I mean, you can make that exponent itty-bitty if you want. Look how small that exponent is. I'm still going to get a value larger than 1. So as long as k remains positive, you're looking at an exponential base that is larger than 1, so growth. And if k is negative, e to a negative power, remember negative exponents make things move across their exponent. They don't make them move across their fraction mark, excuse me. They don't make them negative. But e to a negative power will always give you a value between 0 and 1. It'll be positive always, but it'll be between 0 and 1, and that's how we know it's decay. Cool with that idea? So it is your job to know exponential base e functions are growth when positive exponent or positive number in front of x, or decay when negative exponent in front of x. Which leads us to the next obvious skill, graphing. E is a positive number. It is bigger than 1. And that is why we have the exponential growth function for the equation y equals e to the x. Here's the thing. The number e is an irrational number. And you can never raise an irrational number to a rational. Okay, I'm about to say something that wouldn't have been true. You can never raise the irrational number e, there we go, to a rational exponent and get a pretty y value. There is only one time where e to a number is a pretty value, unless the exponent itself is irrational. Now, I can teach you later in the chapter, I'm actually going to have to, how to find the exponents that would give us e to this power equals like 2. Yes, there are numbers that make it happen, but they themselves are irrational. So you would need this irrational to an irrational, and it would have to be the right kind in order to get pretty values. The only one that is guaranteed to be pretty is the power of 0. Because all y equals b to the x's go through that point, 0, 1, including e to the x. And no other dot on here will be at a pretty place. They're always going to be at awful places. Either the x is awful or the y is awful. One of them is nasty. That's the only place on its entire domain, which, by the way, its domain is all real numbers, where you get a pretty x and a pretty y. So your e to the x graphs will have exactly one place that has a pretty x and a pretty y. They have a horizontal asymptote like all exponentials do. Okay? So how do we graph them then? We describe the transformations, and we figure out how those transformations affect our single pretty point. We figure out where our asymptote was, and we do our best sketch, which you're about to see happen. Here we have e to the x, here you have e to the x, and it's the exact same image on your homework. I gave you the graph of e to the x, and I'm showing you that its y-intercept is at 0, 1. It says sketch the graph using transformations, so what we're going to have to do is list the transformations and what those transformations do. Where there used to be an x, there is now an x minus 2. Can someone tell me what that transformation is? Okay, Thomas? Shift right 2 units. Good. Shift right 2 units. Now here's the real question, because I'm going to have to actually move this coordinate around. If I shift to the right 2 units, does that change my x's or my y's? Lots of people? Hopefully next time when I say lots of people, it's not just 2 people. How about this? Lots of people, if I shift to the right, am I going to add 2 or subtract 2 to my number? Add 2. So this is add 2 to x. This one. So not Thomas this time, somebody else. Come on. I need to know what this does. Ryan? Brock pointed at you, so I didn't know if you were volunteering or... Oh, you weren't pointing at Ryan. You were showing me what it does. Oh, so what's it do? Shift down 4 units. Okay, so does that change x's or y's? Lots of people, x's or y's? Y's, good. And what's it going to do, those y's? Yeah, it's going to subtract 4. Remember, vertical, outside, same. Looks like it's minus 4. It is. Also, because this is an exponential function like all other exponential functions, this number at the back is your asymptote, always. Y equals -4. That is where we're going to find our horizontal asymptote. There it is. Cool. We could find where this coordinate maps to. Right now, it is at, 0, 1. What we've said to do is add 2 to that x value and subtract 4 from that y value. Where that's going to land then is at 0 plus 2, 1 minus 4. It's going to land at 2, -3. 2, -3 is here. That is the only point that is a pretty x and a pretty y. But if you're trying to get an idea of where to draw your graph, you need to ask yourself, was there any reflecting happening? And if the answer is no, then it is still going to go up and to the right. Whee! Like that. If you look at e to the x, it looks like 2, 7 is pretty. It's not. It's just because the line has thickness. But what we can do is we can look at this point that isn't perfect, but we could still say go right 2, down 4. And say, yeah, it'll be about right here. Ish. That's good enough. And then just try to draw your curve so that it crosses through both of them. Things are hard to draw because the pin is in my way. There you go. What do you think about graphing using transformations? Can you pull that off? Because otherwise, you're going to have to grab a calculator and actually evaluate at different x values, and they're never going to be pretty. Okay with that one? All right. Next. Ooh, 1, 2, 3, 4 transformations. Yuck. Let's handle all the outside transformations first. And in case you've forgotten, inside transformations are where the x's are. So since my x's are in the exponent position, the exponent is now my inside area. What are negative signs. What kind of transformation are negative signs? You guys can just shout it out. Reflections. This one's on the outside. That means changes the y values. Changes the y values means goes up and down. Oh, if I go up and down, I must cross over the x-axis. The result that crossing over the x-axis has is -1 times your y value. It multiplies your y value by -1. Whatever your y value was. And then here, I've got a 2 in the front. Shouting out didn't work. I only had one person talk to me, so I guess I have to find victims. Sophie, do you remember when you multiply your y values, vertical, outside, same, what it's doing? I'll tell you, it starts with the word vertical. And it's multiplying, not adding. I chose you because you're short. If I multiplied your verticalness by 2, what would happen to you? You, physically, like. Oh, you'd be taller. So would I have stretched you or shrank you? Oh, vertical stretch. Factor 2. But what does that actually do? It multiplies the y values by 2. Vertical, outside, same. It does exactly what it looks like. And then the last outside change is this one. I think we're all pretty confident with that one. That's shift up 5. And since we already talked about shifting up and down in the previous one, I'm pretty cool with just saying, I think you all know that means add 5 to your y value. Let me squeeze in here. There we go, right there. Yep. Okay. In the previous example, the exponent said x minus 2, and we said shift right 2 units. This says x plus 1, so shift left 1 unit. But if I go left on the x-axis, my number is getting smaller. So what I'm going to do is take my x value, and I'm going to subtract 1 from it. And like the last question, that number that is added or subtracted at the end, this will represent your horizontal asymptote. So I have a horizontal asymptote at y equals 5. I take the one pretty point that y equals e to the x has. And for the x's, I'm going to subtract 1. But look at all the things I have to do to the y. I have to multiply by -1, and then multiply by 2, and then add 5. So what am I actually going to do? I'm going to multiply by -2 and add 5. Sounds like someone was on the phone and they just hung up back there. 0 minus 1 is -1. 1 times -2 is -2. And -2 plus 5 is 3. So my transformed g of x graph has a pretty coordinate at -1, 3, which is here. This time there was more than shifting. There was shifting, there was stretching, but most importantly, there was reflecting over the x-axis. So is that left-right or is that up-down? If I go over the x-axis, am I going left-right or up-down, class? This is an up-down change. If you go over the x-axis somehow, it's an up-down change. So this graph is now upside down. Goes through this point, but is upside down. There it is. And the graph is actually drawn really poorly. I think the y-intercept, I know the y-intercept is negative, so I drew it poorly. But whatever. The point is, you know where the asymptote is, and you figured out where the pretty point goes, and you know which way it points. That's good enough to be able to sketch these graphs and get these kinds of questions right on my tests. So before we go to the word problems, I need to know, is there anything I can answer about graphing skills? No? Okay. Then the word problems. I will tell you that you will never find a bank that offers continuously compounding interest. Who knows why? Not infinite money. It's more money. It's the fastest compounding interest there is. Remember, that was how the number was discovered, was to figure out what was the optimal compounding. And the answer is constant. So continuously compounding things will never occur with banks. But they do happen in reality. They are used in other things. I don't know if anybody is into like forensics or anything like that, but Newton's law of cooling has E in it. It models the temperature of things as they cool down, depending on the temperature they started at and the temperature of the air they're in, things like that. That's Newton's law of cooling, and it uses E's. So it is out there. It's also used in electrical engineering with the complex numbers, like I was talking about in earlier units. Okay. This is not a finance class, though. It's a math class, so I get to do things that would never actually really happen, like savings account with compounding interest, or interest that compounds continuously. This we call the PERT formula. And this is the formula we use for continuously compounding interest. P is still the principal like it was before, E is the number E, and T is the number of years still. The only thing that's different is this R. This R is more like, is your continuous rate. It's not the yearly rate, it's the continuous rate. And remember, if R is positive, growth. And remember that growth is represented by this. So our e to the r would actually be equal to 1 plus r. And if our rate is negative, then it's decay. And decay is represented by 1 minus r to the t. So our e to the k, e to the r would be represented by 1 minus r. These r's are not this r. This is continuous r. These are yearly r. You have to be able to keep those straight. Suppose Tasha invests $1,000 at a magic bank because they are offering 8% annual interest. Whoop, whoop. Compounded continuously. This is definitely a magic. This is a unicorn bank. They don't exist, okay? Right, first, part A of this question is write a formula that represents the scenario. Fine. The amount of money that Tasha has is her initial investment, e to the r still cannot be written as a percent. 0.08 t. That equation models the amount of money that Tasha has in her bank account after any number of years you want. You just plug in the number that you want. Where part B says, what is the constant percent change? Over time, meaning each year. This R is positive. So it's growth. Our e to the power of, I'm going to even artificially segment it, is representing our b value for this. So we have this thing in green parentheses equaling this thing since it is growth. We know that, what's that? No, not me. We know that 1 plus r is e to the 0.08, once again, because it's growth. So if we want the yearly rate, just get r by itself. Subtract 1 from both sides. And we're going to get it as a decimal. Remember, on the battery-operated calculator, you have to type the exponent first, then second ln. On this calculator, I get to do second ln, 0.08. I'm going to close the parentheses to tell my calculator that's the end of the exponent, minus 1, and hit equals. Booyah! 0.0833. I rounded to the first 3 decimals that weren't zeros. Why did I round to the first 3 decimals that weren't zeros? Because I wanted this as a percent. .33 yearly percent. So an 8% annual or an 8% continuous rate is equivalent to over 8.3% yearly. And again, and how I did that was I took my e to the r. I saw r was positive, so that's growth. So this e to continuous r equals this 1 plus yearly r. Because p is p, t is t. E to the r is 1 plus r, continuous rate, yearly rate. Yes, sir?
So for part A, you figured out that like r was greater than 0. How did you do that? Is it like just...
Well, because you're told that r is 8.
Oh, okay.
This r, your yearly r, or your continuous r. If continuous r is positive, it's growth, because it says it's right there. So we knew we were growing, because we were gaining money. Speaking of money, let's see how much Tasha has in her account after 7 years. I'm not actually going to multiply 0.08 and 7. I'm going to let the calculator do that for me. But my battery-operated calculator, people, you have to do that because you have to type the exponent first. So you would do 0.08 times 7, second ln, times 1,000. I'm just going to do this. 1,000 second ln, 0.08 times 7, and I'm going to close parentheses and say, how much money does Tasha have? So after 7 years, Tasha will have $1,750.67. Get back in here, you bodiless head.